أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. يا أيها الذين آمنوا إذا قيل لكم تفسحوا في المجلس فافسحوا يفسح الله لكم، وإذا قيل انشزوا فانشزوا يرفع الله الذين آمنوا منكم والذين أوتوا العلم درجات، والله بما تعملون خبير.
So it's basically license free. The telecom providers need not pay the heavy fees, cost effective. It has a fast turnaround time. And yes, the most important thing that attracts us for FSO is the high bandwidth. FSOs are typically ranging in frequency a very high domain in the spectrum. We are talking about usually around 750 nanometers, 1,550 nanometers wavelength. You can imagine this range allows us for a high capacity or huge bandwidth. And this is what attracts us to use the optical domain. The other benefit it brings with us is the inherent security. So we're talking about a light sensor beam, which is from point to point, and it's not, omnidirectional like the RF frequencies. So it allows us for a concentrated beam to be transmitting the data or information, and also making it secure inherently because it's not omnidirectional. So these two are the biggest benefits that we get attracted to and try to use as a source of our motivation. The other benefits are already listed down in terms of low power requirements, robust to electromagnetic interference, and obviously it's easy to install. Looking at this diagram, at the bottom left side, you can see this is the FCC regulatory that shows how the bandwidth is really squeezed and we are facing a spectrum crunch. And that's why at the top we can see we are trying to explore this region of visible light, which is around 380 to 770 nanometer, and going beyond that with lasers up to 1550 nanometers. So this is where we stand with terms of the spectrum. Now, a little bit of history of light communications. If you see in this diagram over here, you can see light is being used for a source of information or transmitting information as very, very in a long time in history. If you see these pictures as a lighthouse or using light to give information or hinting about something or using light as a reflective source for the soldiers and so on, light is a source of information for a very, very long time, even before what we know as our solar systems today. Who discovered or who, let's say, invented the photophone in 1880, he said he sent his first photophone message at that time, and he used the source as sunlight with these vibrating and parabolic mirrors. And he was able to successfully communicate at a distance of 213 meters. So he wrote in his writings that the greatest invention that he has ever made is basically greater than the telephone. And this is the one that he was talking about, the photophone. So as the ranges, the beauty of optical communications is it is applicable to from the microscopic level of communications all the way to satellite communications. And you can see all of them are listed over here in diagrams. And a lot of work is being done in all these domains. For example, the short range on the chips, we are already using different types of lights, even from Bluetooth to LEDs for inter-chip communications. Even on the body area networks, a lot of we're trying to come out of these cables and have sensors that can use these, healthy, or let's say not damaging light sources that can allow for variable sensor network on the body. Similarly, for personal area networks, today, although our cell phones or mobile phones are not actually equipped with light communications, but there is a lot of research in this recent years where our mobile phones will have a very miniature dongle that will be able to communicate with the help of light source. Now, this was what attracts us a lot because we already have a standard in IEEE that is 822.15 15.7 that came out almost 10 years ago, which is basically using the LEDs or the headlights at the top of your meeting rooms, in your offices or buildings or classrooms, that are not a source of data, because at the back end it gets connected to the routers, and it's connected to the LAN network or the fiber, but from the light, our mobile phones, and we still are able to get connected to them instead of using the traditional Wi-Fi. Now, there has been advancement on this over the very, very recent couple of years, where the same source of light is also being projected to be a source of energy harvesting. So basically, the same light at the top of our heads on the roof are being used for three things, basically: as a light source, as an information source, and also as an energy source for wireless charging. Now, moving to LANs, we can see there are a lot of medical applications where there's a huge amount of research happening of having these medical applications being run by optical networks. There's another one that attracts us a lot is the VANET, or the vehicular networks, since all the vehicles and the source of information for our traffic flow is being done with the help of lights, that is the red, or amber, and green. Now, all these lights can be put to use of not only giving us hints of how the traffic is or when to stop and go, but also to use this as a source of information between each other to tell each other the status of traffic around and what's happening. So basically, it is very complex because it starts involving a lot of angular communications, as we can see on the right-hand side. But this is the beauty of this work. There's a lot of research happening in this direction. Another very attractive domain where this is very applicable is the underwater communications. If you might have seen people projecting ideas over the next decade, how we will have communications happening. So there is one of the propositions where base stations will be co-located, near the peripherals of the land, in the ocean water. So it's not only for a nearby boat communications, but it can go deeper as well, for ship-to-ship communications. And more than that, it can also be used as a source of some sort of sensor network for early depth, or let's say a shallow depth of fisheries, or even deeper than that. So this is again the same thing. You can have inter-networks between ship to air, and so on. This is another great challenge that the researchers have been able to achieve. That is the aircraft communication using optical technology. Obviously, the biggest challenge is these fighter jets are obviously very fast, and basically to deal with this. Are you still able to hear me? I assume everything is fine, so I'm continuing. So basically, yeah, I think so. You're still able to hear me, right? Okay, so I will continue. So basically, yeah, the next one was. The next one is basically the airborne, where we can see there are UAVs being used for communications, and there have been a lot of examples for this. In our lab over here, we also have been able to purchase a couple of UAVs, drones, let's say, where we are going to establish such type of network with 5G setup. This is a projection of scenario by BioLight Communications, where they are able to show us how optical communications will be used from different domains between UAVs, UAV to ground links, terrestrial networks, helicopter networks, and even for surveillance. This is a biggest, move towards using optical technology for space communications, where we can see the European Space Agency have already launched a program called SELEX, where they're trying to have an inter-satellite link between the geo in the geo orbit and the LEO orbit, and that is actually a huge distance that they're trying to cover. Similarly, in more than 10 years ago, in the German TerraSAR X, where we had their first coherent inter-satellite link at a distance of 5,500 kilometers at 5.5 gigabits per second, which is a huge rate as well. Similarly, there are European data relay systems that are also trying to deploy such type of networks in the space. This is another example that took place in 2013, where NASA has its communication link over FSO with the moon. And that's, we're talking about 384,600 kilometers at 622 megabits per second. And you can see at the picture on the right-hand side that that's what it takes in terms of hardware to really have these high parabolic, lenses that will allow such type of communication at such a high range. Again, this is another, idea how we want to move ahead with optical network technologies with space. But more importantly, let's see what's happening here as an example. If you see in the news technology, the light bulbs are being used for trading. Lasers are being used for high-speed trading and stock markets. And this is already happening basically for the past 5 to 7 years. So basically, it is a technology that is secure and fast. Similarly, Facebook had launched in 2014 a schematic for having such type of communication using drones or these Facebook devices or let's say air vehicles that will be also not that'll be charged through solar panels, but will be used as a source of communication to reach the last mile where we do not have successful connectivity for this. So that's another one. And these are the researchers also using the so-called Li-Fi system that's already in place that comes from the pure Li-Fi from Edinburgh, where they have 100 Gbps speeds for your computer with this visible light link. Probably a final example on using VLC in supermarkets. This is already happening in few parts of the world, especially in France, where the shoppers are able to use the LED technology for their shopping and checkout automatically. They don't need any human intervention. So these are the live examples in different parts of the world where they have installed the free space optical devices, and it's showing us success stories. And that's what we want to do more of, and probably make it as a part of 6G very soon. So when we talk about FSO, what happens is basically simple 5 steps, where we have step number 1, where the data, the electrical data is converted into optical pulses. In the second step, you have its transmission happening. That's a laser being projected towards the receiver. In step number 3, the receiver collects these lights through its receiver lenses. Again, it has different types of detection mechanism, which we are going to see in the next couple of slides. And the step number 4 is able to receive the signal converted back into the fiber or copper connected to the network, that is into electrical signals. And we can see at the step number 5, which is basically a full duplex system. So that is the beauty of FSO or optical technology, because it's a pencil beam. You can have a full duplex communication simultaneously, 2 links talking to each other from either side as transceivers without any interference. And this also makes them inherently secure, and you need not worry about the self-interference that happens with the traditional RF system. The biggest problem that we face in optical domain is basically the atmospheric turbulence. And if you see this diagram, you can see there's a formation of small eddies or the small cells, and there's formation of big cells. So again, based on the condition of the atmosphere, we model them into small-scale eddies or small-scale cells and large-scale cells. We independently model them as parameters within our channels for optical communication, and we see how we can perform better and how we can minimize the effects of these formations. So quickly, this is a very simple understanding of terminologies, or the parameters that we use to define the basis on the physical layer for optical domain. The very basic factor that we use the most is the right of variance, and this is what defines our let's say the parameters for the small scale eddies and the large scale formations in the atmosphere. The parameter that defines the right of variance is basically the Cn, which is the refraction structure parameter, which is again defined by the type of detection and the lens formations, the design of the lenses. And then we have the length and so on. We usually study our performances across 3 different regions of turbulence, obviously the weak, the moderate, and the strong. Yes, we would like to have our scenarios, systems working for any type of strong turbulence, and this is the ultimate goal. But sometimes we see it becomes very complex, then we are at least able to give solutions for at least a weak turbulence. And we'll see what happens with these performances in these slides. So just to have a quick glance on how we can comprehend what happens with these turbulence planes, if you see the transmitter transmits a laser beam, which is a source pencil beam, and by the time it reaches the receiver, you can imagine the receiver plane becoming so divergent. And you can imagine logically, even looking at the LEDs at the top of where you are sitting right now, probably, the light source, when it transmits the light, it is in a very small plane and it starts diverging out. And this is what happens over here as well. So the more it starts diverging, obviously we start having dispersion in the power that's being received. And obviously there's a good chance that some of the power will be lost that will not be received by the receiver lens. And this is what happens. So we want to obviously have an ideal scenario where we have a very, very clear line of sight point-to-point communication. But in an ideal, in a practical world, that's usually not possible because of the movements, the beam wander effects, the weather effects. The Earth is having constant earthquakes, which we as humans don't feel, but these lenses do detect them. And these keep moving. So that's why we end up not having the complete, aperture of the transmitted beam on the receiver lens. Probably this is another diagram that can make us understand that this is the source that's transmitting and this is the receiver, and you can see how this divergence region is coming into play. But what if this transmitting source switches or deviates a little bit from this angle? So all of a sudden you will see the whole divergence region is not being received by the destination B, and some might be missing out. So that's why it's very critical that how we take this into consideration and make sure that we're able to receive the acceptable power. So this is another way of looking at it. And the reason why I'm showing this more explicitly again is because this brings another factor in our analysis, which is called pointing errors. And these pointing errors are very critical for optical communications. So this is a lot of text on on the pointing errors in optical communications. Again, I'm not going to bore you with this text, but what I'm going to highlight here is this parameter psi, which defines the pointing error. And the higher the value of psi, it signifies that our pointing error is basically very, very less in the system. It's inversely, this parameter is basically inversely proportional to the effect of pointing error. So that's how we understand this. There's another parameter that we have proposed, that is the parameter R, which basically unifies the 2 major types of detection techniques that are being used for optical communications. The R equal to 1 signifies the heterodyne detection, and there's other one which is the intensity modulation, which is signified by R equal to 2. So the reason for this is, why do we have 2 detections? Again, with heterodyne detection, it's very, very complex to basically implement in the hardware form. It's a hardware complexity that it faces. Although the heterodyne detection brings a very high performance improvement, and we will see that in the next couple of slides, but it has a challenge of implementation. And even till today, as we are having this presentation, the heterodyne detection is not being implemented, broadly speaking, from the industry perspective. So we do not have those off-the-shelf devices as well to study them. So it is a challenge. But intensity modulation, it only looks at the intensity of the light, and you can imagine the intensity of light obviously cannot be negative. So usually our channel statistic is always squared and then taken into consideration. So in that way, we lose half of the domain of discussion of the intensity, and where we're only focusing on the positive side, mathematically speaking. And that's what happens over here. Again, we're getting very good performance of intensity, but you can imagine when we see the results, heterodyne will be way better than the intensity modulation. This is some basic mathematics behind these dependence of the signal to noise ratio or desired power with respect to the detection type. I will not bore you or let's say scare you with this mathematics over here, but what I want to highlight is the equation at the top that basically is the model, or the unified model, probably one of the most generalized ones, or let's say I can say second generalized, because we have some new results that have come out in the literature recently. But anyhow, this is still a very, very generalized solution where we have the pointing error psi, we have the R parameter defining the type of detection, we have our parameter, which is the electrical SNR, or the signal to noise ratio that we desire at the for the successful communication, and we have the instantaneous SNR as well. And then we have two other parameters that are our turbulence, which is the alpha and beta. Alpha defines our small scale communication, and beta defines our large scale fading formations. So keeping these in mind, we will look at some results. Use this model to come up with bit error rate, which is the errors in our channel. And there's a very simple solution, although it looks complex, but yeah, when you see the sit with me, we'll realize it's a very, very easy solution. And similarly, since question might be asked that the G function is basically a complex term that might not be understood by the communication engineer, how it can behave in a real scenario. So to make it easy for our readers and the communication engineers to understand the utility of this result, we took our SNR at an acceptable domain relates to our real life scenario. Usually it's at the higher end, and we were able to deduce our results in simple functions, which makes it easy for us to intuit intuition of the behavior of our results. And that may also come up with diversity and coding games. Yes. No, that's okay, because I was told about 45 minutes. So anyhow, I'll just okay. So basically, there's a change in time. So basically, based on that, I'll just show you some results, which is over here. If you see, the heterodyne detection is, if you see the orange line, for example, even at 25 dB, you can see the difference in bit error rate is very high, even to the power of tens. So basically, heterodyne detection performs way better than the IMDD, and you can see that the magenta and the green lines, the magenta is basically telling us a tough performance, whereas the green one is giving us better performance because of these turbulence eddies. Anyhow, I think since we're running out of time and there is probably a miscommunication on the idea of the timing, I'll just leave you with probably a little thought on how we think about the RF FSO scenarios. If you see over here, as an end user, we want to get to our destination cell of tower to communicate. Usually we can talk to our micro base station with the help of the RF technology, and then use the FSO technology also to communicate. The beauty of the system model here is basically that you're able to communicate without having interference, because this FSO has a completely different frequency range, and it can still keep continuing to communicate even if this RF is communicating, because of having no interference. So we did have some results over here, as you can see. Having only RF system that we have today, and compared to this new technology or new solution that we have provided, we have a huge performance. If you see at the rate of 10⁻⁵ bit error rate, you can imagine we have a performance improvement of around 10 dBs, which is huge for our communication systems. So I think, yeah, with this, I will just quickly jump into a quick scenario that I want to show from basically what we can do in future. So in future, what we can do here is basically imagine satellite systems where we can move into space when we're talking about 6G, and think about how we want to use this optical technology for CubeSats, LEO orbit, MEO orbit, as well as the GEO orbit. So yeah, I think with this I will summarize that we only were able to cover the basics of FSO systems and look at some pointing error and saw a quick performance result. The other topics where we had to jump, but finally we also saw what's the way forward when we talk about 6G and beyond, that we want to look into satellite systems and see how this optical technology will help us reach a better communication system and more improved one in terms of bandwidth and security over the next decade. So thank you very much with this, and if you have any questions, I'm happy to Thank you very much.
Hello, Assalamu alaikum. Can you hear me? Okay. So, Assalamu alaikum wa rahmatullahi wa barakatuh. Allahumma salli wa sallam wa barik ala Sayyidina Muhammad as-Sadiq al-Amin. So, anyway, let me share my screen. Just need to share my screen, but I don't know what's going on here. Yes, I'm going here. Yes, I'm going there, but I cannot. Yes, I know, it's like in the left corner. I can't find it there. Yes. Yes, I can see it. Yes. Yes, I'm clicking this guy. Yes, I think it's not. But yes, but you said you cannot share your screen. I don't know why. Yes, I did click, but you see, you must grant permission in order to share screen. I don't know why. Yes, I go there, edit window, then there. Okay, you cannot share your screen. You must grant permissions in order to share screens. I don't know. Because it's a Firefox. Okay. Okay, go. I did, to be honest. Anyway, let me switch in color. Yes. No, I'm still facing the same problem, to be honest. No, I'm still okay. Let me go to the Google Chrome then. Okay. Okay, just because even I need to download Chrome. We don't have it. I'm using the. Yes, I did. I did this. No, I'm trying. I'm trying another one now. Just wait. I'm so sorry for this mess. Yes. I did. Yes. To be honest, even I have the Google Chrome now. Just wait. I'm downloading the Google Chrome. It's nearly there. Because I don't have the Google Chrome. I'm downloading now, but it's nearly there. All right. We'll copy the link. Or maybe I can see the presentation, then you can. Okay, then I can. Okay, just wait. Done. Yes, I am here. It's still the same, to be honest. Still. Yes, I think. Yeah, I think now it's okay. Yes. Okay. So you can see my presentation, right? Okay. اوكي السلام عليكم ورحمه الله والصلاه والسلام على سيدنا محمد خاتم الانبياء المرسلين. First of all, I'm so sorry for this delay and confusion, and I also like to thank the University of Sabah for having me today with you. Special thanks to the conference chair and the head of the scientific committee as well, and to the audience today. So my name is Ethan Fagani. I'm a senior artificial engineer. I work at the Institute of Telecommunications and University of Aveiro in Portugal. My talk today will be about the 5G technology towards green RF for small cells network. So I try to do it as quick as I can, because basically my presentation was about like half an hour, but still we don't have time, so I try to do it within like 15 minutes if I can. So the outlines of my presentation today. First of all, I go through like a brief introduction regarding the 5G technologies and what are the implications toward the 5G technologies and why we need 5G. Also, I'll explain the frequency or the spectrum bands that the 5G will use in different regions of the world. Yes? I did open. Oh, really? I don't know, because what's it now? Entire. Sorry? Yes, I did. Now it's like as a phone. Can you see it now? Okay, let me go to the. Okay, just wait. So shall I do it like entire screen, right? Yes, entire screen. Just wait now. So can you? Yes. Yeah, no, it's there now. Is all right? So shall I start from beginning then? All right then. So as I said, because we have, so you can see it now, right? All right then. So let's go. So as I have said from beginning, my presentation was like managed about 13 or 35 minutes, but now I will do it like I'll do it a bit fast, and I will try to make it with like 15-20 minutes. But anyway, my outlines today will be about the 5G technologies. I will talk about the 5G and in terms of like requirement and what we need 5G and what 5G will change in our life. Plus, I will talk about the motivation of the 5G, and I will mention also what kind of frequency or spectrum bands that 5G will use, the spectrum choice and network outcomes, and what will the 5G enable or what will drive to the society, what kind of new services 5G will bring, target and use cases, different use cases like medical and education, societies, and different things. Then after that, I will check with you together what kind of or what experts says regarding the safety and health concerns regarding the 5G spectrums. Also, I will go through what's the greatest network challenges for the 5G era. Then after that, I will talk about one of the projects that we are coordinating now with the other European partners where our part or our work will be dedicated to the RF components or RF front end for 5G handsets. In particular, I will talk about the antenna design and filter design. Then I will conclude of my talk, and I will go through like a brief future work of the technology. So here we go. The 5G, as everyone knows, is the 5th generation of the mobile networks that's considered as a significant evolution of the 4G. The 4G LTE network, which is existing now, the 5G will have more advantages than that technology. It will be faster. It will be able to handle more connected devices, and that will go towards the improvement that will enable a wave of a new kind of the tech products. So the 5G introduces a huge technological advantages like a high data rate, which is large bandwidth, very low latency of 1 microsecond, ultra reliability, and that will be when and where is needed. As you can see here in this pictures, that's the generation of mobile phones since 1980 up to today. So in 1980, just we used to have like analog voice or just calls. Then after that, we have like call and text, which is digital voice. Then we went through the 3G in 2000s, which is mobile broadband. In 2010, we had the 4G technologies, which is better and faster mobile broadbands. And now the idea is to connect the society, and that's the 5G era. The 5G era is to digitize the society or to connect the society all together. So that's one target of the 5G. But what are the motivations or stimulations toward the 5G? Although, and as we know, the 4G system are being deployed all over Europe and even worldwide, also this kind of technology have made a great progress, like mobile broadbands, ubiquitous service is everywhere at any time, enhanced support of the Internet of Things, and also more advanced and progress are still continuing. But as a number of connected devices will be increased daily, and also more stringent quality of service requirement like high data rates, low latency, large volume of traffic, and large bandwidth and more capacity is needed. So we need to think about a new technology that can meet this kind of requirements. So a common agreement that incremental enhancement of the current network paradigm will not come closer to meet the requirement of 2020. So the solution here is to think about a new generation of networking system, which is the 5G. And here is the answer of the questions, maybe why do we need 5G? If you look at this picture here, and this kind of huge connections everywhere, like industry automations, smart factories, smart health, 3D videos and voice, self-driving cars, and a lot of connections, smart hospitals, smart, everything is there. So basically, we need to think about promising networks that can help to securely connect the society together. So that's why 5G is needed. Although the 4G has brought a kind of promising outcomes and result and good connections, but still we need to improve it to go through the 5G. The questions here, does 5G need one frequency band or different frequency bands? But since the 5G will serve different services and applications, so that's mean that we will need a different kind of spectrums to meet that goal. So here, and according to some communication body or regulators bodies like Ofcom in the UK, the 5G will work at different frequency bands or different families. So the family number one is like spectrum at lower frequencies, which is at 700 meg, and this one, of course, will give us like a large coverage of wide area. It's working at a lower frequency. And the another one is like spectrum at higher frequency, which is less than 6 gig. They call it FR1. This one will provide the necessary capacity to support very high number of connected devices today. And there is another kind of frequency, which is a very high frequencies above the 24, which is the millimeter wave spectrum. They call it FR2, with very large bandwidth, providing high capacity and very low latency. But the cells at those kind of frequencies or spectrums will have a very small coverage because they work at a very high frequency. So it's likely that built out the 5G networks in millimeter wave. And this will be focused in the area one or to specific locations, premises, requiring service with the very high capacity. So this will be like indoor communications or indoor scenarios. Here's the spectrum choice and the network outcomes. The 5G brings such unprecedented spread of spectrum, and that's just, we need to think about that. The 5G is not longer, longer to think about it as a single networking. No, the choice here is the different spectrums will determine whether the network will deliver only coverage at the lower band, for example, like here in this figure at 700 meg, or just we need to think about the capacity, which is at the millimeter waves spectrum, or just we need to compromise or make a kind of trade-offs to get this and that, to get the capacity and the coverage at the same time. Therefore, the Europe spectrum managers have defined 3 different frequency bands, as I said in the previous slides. So as you can see here, the capacity and coverage will be for the lower band and up to 6 gig, and for the millimeter wave, that frequency will give us a very good capacity. So that's why the 5G can gather or can get both factors, the capacity and the coverage at the same time. And this is one advantage of the 5G technology. Also, there's another question here. What will the 5G enable? What will the 5G do for our life? What will change in our life? The 5G will enable the future digital world. The 5G will enable instantaneously connectivity to billions of devices together with the Internet of Things, and that truly will lead us to the secure connected world. As you can see here, this is the healthcare, smart energy, cars, smart educations, smartphones, smart homes, and everything. So the 5G will connect all that together and give us a new opportunities that we don't have in the previous generation of the 4G. The 5G drivers or the opportunities that the 5G will bring to the society. User experience continuity, which is high definition videos, and teleworking will be commonplace and available anywhere. Like what happened now within the coronavirus, the pandemic of the coronavirus, we all of us we are working, or we are doing our home as a teleworking for like 6 months now. So that's one advantages of the high speed technologies with the secure connections. And the 5G system also will provide user access anywhere, which will leverage the legacy platforms technology like Wi-Fi, 3G, and 4G. And there is another enabling, which is the Internet of Things, a platform to connect the massive number of objects to internet, like sensors, actuators, will spread anywhere. And also the future of smartphones, drones, to be used in different kind of sectors, robots and wearable devices, especially that will be used in the medical applications to monitor, to watch the old people, to patients, and so on. Also to check a lot of things using those wearable devices. And another thing is also the mission critical services, which is also very, very important, like the public safety services that's used in Europe and worldwide, like Terra and Terraball. For example, when something happen at your home, like if there's a fire or there's a kind of crime, so instead of calling the services and explain everything over the phone, they can share a video with you, and they can be like live in the incident that's happened at your home, or even they can use drones to take some videos and to get like the clear picture. Also, there is another service which is the requiring real-time activities like vehicle-to-vehicle communication, vehicle-to-road, and also other services that will pave the way to the self-driving cars or autonomous cars and smart factories and also remote health services. So here is the 5G targets with some use cases like smart farming, where we can use the drone spraying, weed and crop monitoring, insect tracking, reduce water consumptions. That's all can be done by using the 5G technologies over the traditional and conventional ways or manners. Also smart educations like smart classrooms to save the future time, the teacher time, learning from distance, like what we do now for our schools over the pandemic of the coronavirus. So they do everything over the internet. Also smart banking to improve the security and the fraud prevention, which is very, very important, and also to improve the customer service. Smart health, like to remote group consultations, remote ultrasounds. So basically doctors and consultants, they can see everything while they are not in the hospital. Also smart transportations like autonomous cars, connected bus stops and vehicle tracking systems. Smart energy, which is very, very important, like smart grid, smart meter, remote monitoring and remote emergencies rescue. Okay, but now after we have seen all the advantages and the enablers and the targets and what 5G can do for our life and how can change our society completely, but just there's another question which is always raised among the public. Does 5G save or does 5G pose health risks? As you can see here in those pictures, imagine someone is there and everything around you is being or every device around you is being connected at any time and anywhere. So of course, this kind of large radiations from those connected devices might make some risks or might bring some risks to your life. And also an increased number of connected devices, which is by 2020, which is this year, there's expectations of 50 billion connected devices. So the question is, are we safe with this technology, or are we safe with using this kind of technologies, connected our devices, smart watches, smartphones, smart tablets, TVs and cars and everything? So let us go and see what the experts say about the 5G and health. As you know, all the wireless devices, because before they sold and enter the market, they should go through a formal government approval process to make sure that they don't exceed the maximum of SAR. SAR, this is the energy is being absorbed by the body. So according to the Australian agency and the European Commission, as well as the American Council of Society and WHO organizations and the FCC in the US, and even the Ofcom and some other communication bodies in the Asian like Japan and China and Korea, till today, they say there is no evidence that the 5G technology will affect our health. So far we are secure, but they don't confirm that. They say up to date we are okay. So that's mean the 5G technology is quite all right, and there is no clear effect in our health. But when the coronavirus popped up a few months ago, there is a kind of say that there is a link between the 5G technology and the coronavirus. They say using the towers and the cells of the 5G, they can be a cause of the coronavirus pandemic, but still no such evidence there. It's still all of that research and stories. So what's the greatest network challenges for the 5G? In general, there are top 5 challenges, which is frequency bands, very, very important. Deployment and coverage, very, very important as well. Cost, device support, and security and privacy. So of course, we need to get secure network and we need to ourselves to be secure. But according to the IET executive summary in the UK, they say the greatest network infrastructure challenges is coverage. And the British government and the Ofcom body in the UK need a place to coverage maximizations, or they mention something like the coverage maximization. They need to increase the coverage at the top of the list. And the coverage, when we talk about coverage, not only getting signal for voice call anymore or anytime, but getting the necessary quality of service to digitize our society. So that's the meaning of the coverage here. The meaning of the coverage, just to get something or enough coverage to digitize our society. So what the types of base station are used ones they use for the 5G? The best base station that use or that can be considered as a good candidate for 5G is said to be the small cells. And the key success for the small cells, which boost the quality of services in wireless network, is their high frequency components that draw upon a number of different technologies. So that's why the small cells base station, the lower powered base station, the small ones that can be used indoor, will be the major features for 5G network, particularly at the new millimeter wave frequencies, which is the FR2, where the connection range is very short because of the high frequency, so we can get very short coverage. That's why we use those kind of spots or small cells to improve the coverage. And of course, will be like a kind of complement of the macro network that being used in the 4G technologies, which lead us to improve the network capacity, improve the extended coverage. And as you can see here in this photo, this one is the 4G LTE base station, which is the macro base stations. They are not using the massive MIMO antennas, so the coverage is like everywhere. And sometimes one of those users, they cannot the coverage because of the non-sight of light, because of those buildings, and there are a lot of obstacles. And also there will be a waste of power in unwanted direction or unwanted places. But here in the 5G technologies, we have been using a massive MIMO antennas with beamforming system, so we can steer the power or the radiation to the users while not wasting the another power or radiation in the unwanted directions. While we are also placing a number of small cells that will help to get more connection and secure connection to the user everywhere. As you can see, the capacity of the 5G is being increased compared to the 4G and 4GA. So how people connect in urban areas, because the small cells basically, they can be used indoor and outdoor, but they prefer to be indoor, and they prefer to be in urban areas because in the very large coverage, which is better to use the lower frequency bands, because of villages and those kind of places and like isolated cities, it's good to use like a lower frequency maybe to get more coverage. But even after kind of like modification and improvement, the small cells, of course, they will be deployed in the rural areas. Here we have like three kind of key offerings for the small cells. Indoor small cells, as you can see here, like in offices and schools and those kinds of things, will deliver high performance indoor wireless. Indoor small cells solutions are designed to satisfy the demand of data hungry users. And the another kind is outdoor small cells to boost the outdoor connectivity. Outdoor small cell solutions will be an integral part of delivering high-speed connectivity to your subscribers, as you can see in small streets. And also there is another solution or another kind is street solutions. Enhance the street coverage in the busy streets like in New York or London or those places. So connect urban subscribers as they commute, the people who are commuters to come in and come out, work and play. The small cells can be the solution on those kind of streets. And in this figure, is clearly shown that between 2017 up to 2025, the small cells technology will be used more indoor than the outdoor. Okay, now we'll go about the RF part. Well, that's our area of research recently with our group here at the Institute of Telecommunications. I will take you through one project that we are coordinating with the other European partners. The project called Secure Network Coding for Reducing Energy Next Generation Mobile Small Cells. And the abbreviation of that project is like SECRET. So the reason of this project, or the aim of this project, is to narrow the gap between the current technologies, network technology, and foreseen requirement of 2020, which is the 5G technology. In order to deliver high networking capacity, ability to support more users, more connections, low cost, and hence energy efficient, and of course with the target of secure connectivity. So also there's another objective of this project which aims towards the new deployment of small cells based on nation of mobile small cells. This project we submitted in 2016. The Marie Curie project is being accepted in 2017. Now we are doing this project for like 3 years. We are at the end, but because of the coronavirus, we get like more 6 months extensions. The idea of this project is like to hire a PhD students. We had 13 PhD students, and we call them like early sales stage, which is ESR. We train them because the idea of this project is like a training project. It's like vehicle for them from the PhD stage to the research or postdoc stage. So we train them and we get them ready for their future careers after finishing the PhD. There are 5 countries involved in this project: UK, Finland, Portugal, Germany, and Greece. And there are 8 partners, 4 from industries, like Sales Technology Company in the UK, a Brohoff company in Portugal, Huawei Technologies in Finland, and Acticom in Berlin, Germany. And there's like 4 academics partners: University of Bradford in the UK, IT, we are in Portugal, University of Dresden, Germany, and University of Patras in Greece. This project has been divided into like 7 work packages, different work packages. WB1 is like the project management, where we manage, and we are the coordinator here, where we manage our project outcomes and meetings and so on, and the websites. And WB2 is like network coding cooperation for small cells. WB3 is secure network coding for small cells. WB4, and this is the one we are dedicated to, which is a green RF for handset, 5G handsets. WB5 is like enabling mobile small cells and network virtualization. WB6, which is the training, this one is just to train the ESRs or the students. And WB7 is the disseminations. Dissemination is like to publish some like conference paper, magazine, journals for the academic partners and for the industry partners, just to get our prototypes or our designs to standardize them and commercialize them and take them to the market instead of being in the shelf. So, as I said, I will talk today about the WB4, which is the green RF. This work is being divided into 3 tasks: a green power amplifier, a tunable filter, and antenna designs. Also, I will talk about only 2 tasks here, which is the tunable filter and the antenna designs. Yes? Okay, I'll go. Oh, anyway, I will try my best to go as fast as I can. So this is one antenna design that we have done within this project. It's like MIMO antenna design, very small antenna, very compact, using different kind of techniques like square slot in the ground plane to improve the isolations and the mutual coupling between the 2 antennas, as well as we use like 2 rings to bring the frequency down to our 5G target frequency 3.6. As you can see here, this is the idea of the using two rings. This is the one without, not interested. This is the one with 1, not interested. One with the 2 rings, very interesting and showing very good result and meet our frequency targets. This is the parametric studies that we do in order to get the optimum and final optimized design before we take it to the fabrication. After we get that, we take it to our lab to fabricate it, to measure it inside the lab, RF lab, with the network analyzer, and we measure the radiation pattern again inside anechoic chamber room that we have at our universities. We have got very good result here, as you can see, very good gain, very good efficiency. Then after that, we place, instead of 2 antennas, we place 8 antennas to be like a MIMO. Then later on to do it like massive MIMO to be used for the small cells and 5G technologies. So that's the idea of designing those kind of RF components. Okay, this is the antenna fabrication. Also, we take it to the lab and we measure it. Also here, which is very, very important thing, we measure the SAR of the antenna to see the side effect and how much power is being like transferred from the antenna to the human head. And we have shown very good result, which is 1.4. That meets the American and the European standards. This is another kind of antenna, which is 4 MIMO antenna. We start with a single element at 35 gig. This is another frequency, which is millimeter wave. Then we use 2 elements, then 4 elements, which is showing very good result here, 35 gig frequency is 11 with the very high isolation, which is around 30 dB. So that's mean the antenna is well isolated and there is no power going from one element to another. Then after that, we fabricate the antenna as well. We test it inside our lab. This is the one of the filters that we have been used, bandpass filter, working at the 3.6 UK 5G like band, showing very good S11 and very good insertion loss less than 4.2 dB. Or tunability. Instead of having one device that can one band, we can tune this band and make it multiple band within the same device, without changing the filter geometry, which is very good process. This is one of the filters that we have been designed for the configurability or tunability mechanism. By changing the capacity of the capacitor that we have placed as a varactor, you can see from 3.8 up to 3.4. So we can cover like 4 or 6 bands within one device and without changing the geometry of this device. This is another filter as well. We have used the varactor diode to achieve or to accomplish a very continuous wide tuning range. As you can see here, and this is the filter prototype with the tuning circuit, one cable for the DC to change the voltage of the varactor and one to the ground. We have moved the frequency from 3.6 up to 2.6. So in this filter, we can use it for both technology, 4G and 5G technologies. Okay, so after that, just we need to think about the massive MIMO base stations. As you can see here, this is the 4G macro. They are not using MIMO mechanism or MIMO technologies for the small cells. But in 5G, we have been, they use the MIMO technology with the beamforming. So instead of the power is going everywhere and wasted sometimes, just we can direct it to the where is needed. Like we have a lot of beams here, so no loss. But if you can see, this power is like omnidirectional, it's going everywhere, but sometimes we don't need it everywhere. So we'll have like kind of wasting of power. And here also the same thing. This is another antenna, but the time is not allowed. So anyway, this is like antenna is working at 60 gig, which is very, very high frequency. This is a array antenna design. This is the single element. Then we make it array. We make array with like 32 elements, 32 antenna, and we can control the radiation pattern. So each sector has different radiation from the another. As you can see here, we have like 8 radiation patterns, and that's very promising design to be used for the 5G small cells. So the summarized conclusion here, just we have been giving a brief visit on the 5G technologies in terms of motivations, the choice of spectrum, what 5G can bring for us, how can change our life, and also we have stated some issues regarding the health concern and what the expert says regarding this. we talk about the small cells in securing the connection of 5G and how we can get use of it. We have also mentioned some of the RF components that we are doing for our project, SICTED project, especially the antenna design and filter designs. And here we take you through the future work that maybe we are thinking now about the new era, which is 6G era, because the 5G, yes, is not like standardized yet, but there are a lot of work on the 5G. So now engineers and academics and industry, they start thinking about the 6G, which is the next hyper-connected experience to every one corner of life. The target of the 6G to support microsecond of latency, which is much better than 5G, 1,000 times faster, and high data rates of 1 tera. But what is the candidate technology for the 6G? Because in 5G, we focus in the millimeter wave technology, for example. But here in the 6G, the terahertz technology will be the best candidate. And of course, in terms of the antenna design, so far, the best antenna design for the 6G is the graphene antenna. So instead of using the normal radiated element like a copper, we need to use a graphene because of the high conductivity. So that will improve the antenna gain and the antenna efficiency. And that's only still at the beginning of the journey. So we start the journey. And the 6G timeline for 6G is expected that the ITU will begin their work to define the 5G vision in 2022. It's expected that the completion of the 6G standard and its earliest commercializations could happen as early as 2028. So basically, we still have 10 years to think about it. So thank you very much for your listening, and I'm so sorry for the delay on the. Yes. Sorry, can you say? Okay. For example, let me talk about the efficiency in terms of the antenna design. For example, our target to get the good efficiency in the antenna design, for example, because that's what we are doing in our research center, is to implement some kind of techniques to reduce the surface radiation, because there will be a radiation in the surface of the device, and once we reduce this, that will take us to improve the gain and efficiency of the device, and that, of course, will improve the gain and efficiency of the system as a whole. And anyway, my email is there, even for the audience or other guys if they need to ask or get any kind of like explanation, my email is there, so they are welcome. Thank you very much for your listening. Thank you.
استاذ سلوى عندي سؤال لو سمحتي. عندي سؤال.
Yes.
استاذ سلوى عندي سؤال لو سمحتي. Thank you, Dr. Isa, for your presentation and good cover for the up-to-date. I have two questions. First question about the base station.
Yes.
The quality, how in 5G technology to measure the KPI? Is it different from the other technology, for like 4G or the traditional network?
I cannot hear you.
About the base. Sorry?
I cannot hear you.
Okay, I'll come again.
Just
about the base.
Yes.
Do you hear me?
Yes, yes, go ahead.
Okay. My question is about the base station.
Yes.
The quality performance, the KPI, measure the KPIs of the network base station. What is the main KPI to see the quality of the quality performance of the network for mobile or for the internet? Is it different from the 4G and the other?
Yeah, the different in terms of base station between the 5G and 4G will not be like a huge difference, because in the 4G they use the macro cells, and the 5G they use the small cells or the micro cells. So basically, the difference will not be that much between the 4G technology and the 5G technologies. But there will be like a small kind of improvement, because in small cells they cover more area than the macro cells. That's the only difference between the base stations in terms of 5G and 4G.
Yeah. So other question about you mentioned in your presentation five challenge for the network. About the coverage, diplomatic and coverage point, is there improvement using optimization or AI algorithms?
Yes. That's what our partner in the project they use. Our partner from the network side, they use for improving the optimization. They use algorithm, they use optimization techniques for this. But as I told you from the project, we are from the RF side, so we are doing the RF front end. But our team, they are doing a new algorithm and the new techniques to improve and to optimize the network performance.
Yeah. Thank you, Dr. Isa, for your answer.
And if you need even something more about this kind of networking, so you can email me, and even I can talk more about the team at our group.
I am doing communication network in Libya.
Yes.
To see the performance quality KPIs for the network.
That's very good. So you just email me, and I can link you with the networking team at our group.
Okay, thank you.
You are welcome. Thank you very much.